darling. I lost my friends. I lost my mind. I lost my baby. I lost my darling. I lost my friends. I lost my mind. Pour une fille d'Ottawa, grandie à Sainte-Foy, d'un père militaire, et d'une belle fille qui fut sa mère, qui écoutait du country, entre deux caisses de bière, et partait le samedi, pour un lac d'Oxbury, rejoindre la grand-mère, un autre famille, un autre famille. Or je ne peux vivre sans toi, et je ne peux vivre avec toi. Mais tu peux très bien vivre sans moi, je suis tu dans les deux cas. I lost my baby, I lost my darling, I lost my friends, I lost my mind. Coup de fil de Jamie, qui un jour tomba pour une fille d'Ottawa. Quand il je ne sais pas, d'un père pilote de l'air et d'une mère je ne sais quoi, tous deux aimaient le cinéma. Nous sommes habitants de la Terre, et il y a des milliers de frontières. Quelqu'un existe dans l'univers, pour quelqu'un d'autre, et c'est la guerre. I lost my baby, I lost my darling, I lost my friends, I lost my mind. Pour une fille d'Ottawa, grandie à Sainte-Foy, et qui un jour tomba pour un chanteur populaire, grandi en Algérie, à s'époque et merci, et qui lui dit adieu, je repars faire ma vie à Oxbury, à Oxbury, à Oxbury, à Oxbury. I lost my baby, I lost my darling, I lost my baby, I lost my darling, I lost my friends, I lost my mind, I lost my baby, I lost my friends, I lost my baby. À quoi je joue? Je joue de la guitare. À quoi je joue? Je joue de la guitare. La solitude parfois est immense, plutôt que d'être ce passant qui tente un seul temps de temps en temps. Alors je pars à la dérive, mon lit est un navire, un atelier où je vais pour l'éternité. Hier jeune homme instant présent, je ne sais pourquoi je suis si triste. Je me rappelle quelqu'un m'écoute, je me sens seul quand je viens tout nous faire. Quand je joue, je joue de la guitare. Quand je joue, je joue de la guitare. Je sens que j'hallucine et j'ai peur de partir comme un fou vers le monde. J'ai des grands instants de lucidité. 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 But the system, do it, yeah. The system, do it, yeah. But the system, do it, yeah. But the system, do it, yeah. Choisir entre tous les gens qui m'entourent. Comment faire le dame? But the system, do it, yeah. But the system, do it, yeah. J'ai des grands instants de lucidité. Et j'ai des grands descends 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 de lucidité. J'ai des grands descends de lucidité. Et j'ai des grands descends de lucidité. Je joue de la guitare. Je joue de la guitare. Faisait pas beau dehors, she wasn't a whore. Avait de pardonner, cherchait à discuter. Peut-être qu'elle avait le sida, peut-être qu'elle ne disait pas. Comme la neige à neiger, ma vie est un jardin, j'ai tout l'envie que j'ai. Pleurer oiseau de février, tous les étangs gisaient, je l'ai donné. Fuck the system, do it, yeah. Choisir. Pourquoi je joue de la guitare. Pourquoi je joue de la guitare. Je sens que j'hallucine et j'ai peur de partir comme un fou vers un monde. Et j'ai des grands instants de lucidité. Et j'ai des grands instants de lucidité. Il y a les sirènes qui chantent les marées. Il y a les sirènes qui chantent les noyés. Vers les îles. C'est le temps d'embrasser les fleurs de cimetière. C'est le temps de mourir. À la guerre comme à la guerre. C'est le temps de partir. C'est pas pour te prendre. Do it. À la guerre comme à la guerre. Dans son silence, un poisson lune. Il se fait au fond des brumes. Mais jamais Nemo ne saura. Et doit penser du poisson-chat. Dans son silence, un poisson lune. Philosophe est au fond des brumes. Mais jamais Nemo ne saura. Et doit penser du poisson-chat. Les sous-marins se font la guerre. Sous les tropiques du cancer. Mais jamais Nemo ne saura. Et doit penser du poisson-chat. Encore. Jamais Nemo ne saura. Et doit penser du poisson-chat. Choisir entre tous les gens qui n'en sont pas.
Seems to be many questions about this. What's going on here? This is not a difficult question. We're looking for the second derivative of 0. The only trick is to notice that when x is 0 here, y has to be 1. That's the first thing you need to notice. And then you just differentiate implicitly. Twice, in fact, because we are looking for the second derivative. Somebody was asking about identities for the midterm. I mean, you should know them. But again, midterm is open book, open internet, so it's not an issue. It will be an issue for the final, though. Final is scheduled to be in person, and I strongly believe it's going to stay that way. So you need to know everything. Speaking of the midterm, I've posted a mock midterm, really just to get you acquainted with CrowdMark. It's one question from the tutorial, in fact, that was going to be on the final, but the head TA beat me to it, so I left it in the tutorial. So really, it's just to get you acquainted, first of all, with the with the CrowdMark system, and making sure that you can upload your answer quickly. So have a look at that. The midterm is actually 2.5 hours, right? It's supposed to be a 2-hour midterm, and you'll have an extra half hour. Yeah, so first of all, that mock midterm opens up tomorrow morning, I believe, at 9 a.m. You will get an email from CrowdMark telling you can access the thing. If you do not get an email tomorrow, please email me. I'll see what's going on there. Yeah, so you'll have 2.5 hours. It's more than enough time. On the far right, how did you go from the first line to the second? From here to there? All I did was differentiate. I differentiated the whole equation. Derivative of the left-hand side is the second derivative. Derivative of the right is the quotient rule, right? This minus that all over this. Yeah, nobody's seen CrowdMark. Well, I mean, I probably shouldn't say that. I don't expect you to have seen CrowdMark. You will get an email from CrowdMark. Are we allowed to use tablets and upload screenshot? That's fine. It does not have to be on paper. You can use a tablet. How did you get -1 for the first derivative and not 1 over e? Have I made a mistake? I have made a mistake. I have made a mistake. Thank you. This is -1 over e. For some reason, I was using y equal to 0. Thank you. Thank you. 1 over e, -1 over e, right? -1 over e. So then here we have a mistake. So this is going to be 1 over e then. And probably more than that. If x is 0, y is 1. So this is e times negative. Oh, so it does turn out to be 1. So 2 mistakes which had somehow cancel themselves out. That's unexpected. And here, this was 1 e times, so that should be 1 minus 1. Oh, so the whole thing is 1. All of this work for 1. Thank you for noticing that. Format of the midterm, long answer. All long answer. How many questions? I haven't written it yet. I'm going to do that sometime this week, hopefully before Thursday. The reason x is 0 and y is 1, well, x is 0 was given, right? We're looking for the second derivative at 0. But they only gave you x equal to 0. The question arises naturally, if x is 0, what is y? And if you plug in x equal to 0 in this equation, you immediately see that y has to be 1. Well, I mean, it's always true, right? I mean, if x is 0, y is 1, it's a function, and there's no hesitation here. You don't need to know how to graph derivatives. All right, moving on. Somebody was asking about limit as x goes to 0 of root x. As it is, this does not make sense. That's the answer. Because you know that as x goes to 0 from the left, if you're taking negative numbers, this is not defined. So only this makes sense. Again, I have not written the midterm. I don't know what I'm going to put there yet. I have a few ideas, but that's it. Last time we were talking about, so music today brought to you by Jean-Loup. Ran out of time, but there is a connection with Brand Van that we listened to on Friday. The last song I was going to play you was co-written by James DeSalvio from Brand Van, but too late now. Jake's asking about this question, and I think somebody answered that already. Multiply by the conjugate. Multiply by the conjugate is the right answer. Yeah, exactly that. Paul is asking if it's unwise to do calculation questions as practice, seeing that those won't really be on the midterm. Not unwise, because that's how you're going to master the material. And mastery of the material is what I'm looking for. If you are very comfortable with those types of questions, the harder, more theoretical questions are doable nonetheless. Even if you haven't seen them before, even if you haven't practiced. And Jake's question is a good midterm type of question. Asking us to find the limit of the difference of square roots where you have both a and b. So, yeah, all right. On Friday, we were talking about inverse functions. We defined the concept of inverse functions and everything. And we saw that very much like a vertical line test, to determine if the graph that you have is that of a function, we have the horizontal line test to determine if the graph you have is that of a one-to-one function. And a function has an inverse if and only if it is one-to-one on its domain. So what I want to bring your attention to is this function. Right? I mean, again, you're very familiar with this function. of minus 2 is 1/4, and so on and so on. The inverse function, if it exists, is a function that sends 1 back to 0, 2 back to 1. 1/4 is -2, and so on and so on. Let's graph this function. Y equals 2 to the x. You know what the graph of that looks like. The graph of that is just an exponential function, 2 to the x. And this function, by the vertical line test, horizontal line test, sorry, by the horizontal line test, is easily seen to be 1-to-1. Have I made, geez, I keep using y equal to 0 in the previous example. You're probably right, Halen. So sorry about that. Yep. And Eddie got 1 over e squared. I see my mistake. I kept using y equal to 0 when in fact y was equal to 1. So thank you. Make the change. All right. 1-to-1, right? Injective, and consequently it has an inverse. This has an inverse by the fact that it's 1-to-1. So if you interchange x and y, you see the issue. There's no way for you to solve this. Right? You know how to solve for the inverse, but there's no way for you to do that here. And yet the inverse exists. So we give it a name, and we call it the logarithm. Thank you. Thank you, Jake. We call it the logarithm. The logarithm is the inverse function of the exponential. We know the exponential has an inverse. So we give it a name and we call it the logarithm. And how are functions and their inverses related? Right? If this is the graph of the function, to solve for the inverse function, you just invert the x and the y axes. So if you invert these and graph it in terms of x and y again, right, for large negative values of x, y is close to 0. So for large negative, so if you interchange these, for large negative values of y, x is close to 0. And then as x gets larger and larger, so does y. This is the graph of the inverse. In other words, what's happening? You're just taking a reflection about the line y equals x. You're interchanging the x and y. It's a mirror image about the y equals x. Yeah. About the line y equals x. Joe's asking an excellent question. If a function is 1 to 1, is their derivative also 1 to 1? The problem is, a function being 1 to 1 does not imply that it is actually differentiable. So now let's Sophia's asking there's never a y-intercept for the log function, and that's correct. Right here, you know that the range is 0 to infinity, not including 0. So the range of the exponential will be the domain of the inverse of the logarithm. Let's go back to Joe's question. Right? A 1 to 1 function doesn't have to be differentiable. But now, let's ask the question if it's 1 to 1 and differentiable. What about their derivative? Or, let's ask this question. If f is differentiable and injective, what can be said of the inverse? What can be said of the inverse if you have a differentiable and injective function? In other words, if I have y equals f inverse, what is the derivative? The inverse is differentiable, absolutely. Are logs always a perfect mirror of the exponential function in the xy line, x equals y line? Indeed it is, yes. In fact, a function and its inverse are always mirror images about the line y equals x. So we have this. Let's take f of both sides. And we get f of y is f of f inverse of x. But f of f inverse, the composition of a function and its inverse, you know what that is. By definition, this is just x. So we have f of y is equal to x. Now let's differentiate this equation with respect to x, assuming y is a function of x, which it is, right? Because it's right here. So implicit differentiation, what do we get? What do we get? We get f prime of y times the derivative of the inside, chain rule, dy dx, and derivative of x is just 1. So immediately we see dy dx is 1 over f prime of y, and y was originally f inverse of x. And there we have it. Take f of both sides. So f of y is equal to f of f inverse of x. That's what I'm doing here. I'm doing the same thing to both sides, so equality is maintained. So here we have it, dy dx, the derivative of the inverse is 1 over f prime of f inverse of x. Very nice. Now let's apply this. To the function e to the x. The function e to the x, so that its inverse is log base e of x. And this happens so often that we give it a name, and we call it the natural logarithm, or the ln function. Left bottom to the top right, I differentiated. I'm differentiating with respect to x here. So derivative of the left-hand side, what's on the left, it's f of something. So the derivative is f prime of something times the derivative of the inside. Derivative of x is just 1. Right, so we're going to apply this formula here for the derivative of the inverse to the case where we're taking f of x is e to the x. If f of x is e to the x, you know what the derivative is. Its derivative is, once again, e to the x. And the inverse is ln x. So really the question is, what is the derivative of ln x? Well, the derivative of, so this is the derivative of the inverse, which we just saw to be 1 over f prime of f inverse. So here f prime is e to the x. F inverse is ln x. So this is 1 over the derivative with x replaced by ln x. So this is 1 over e to the ln x. But what is e to the ln x? E to the ln x is the composition. Is the composition of f and its inverse. And you know, right, because this is f of ln x. And so this is, everywhere you see an x, in e to the x, you replace with ln x, and you get e to the ln x. So this is the composition of a function and its inverse, and you know that this is actually x. Thank you, everyone. And there you have it. The derivative of ln x is 1 over x. the derivative of ln x is 1 over x. Look, we're using what I've just erased here, that the derivative of the inverse is 1 over f prime of f inverse. And all you need to do is plug in these things for where they apply. F inverse is ln, f prime is e to the x, so there it is. You could use this rule to find the derivative of arc sine, absolutely. Again, you don't need to prove it every time you use it. We've proved it once now. So we're going to make use of this from now on. Let's take a few examples. Well, before we do that, let me generalize. Can we generalize? What is the derivative of any logarithm for a bigger than 0, a not equal to 1? Can we generalize to any logarithm? And how do we do so? Well, we have the change of base theorem. Change of base theorem, which tells us that log base a of x you can change to any base b using this formula. Right? This is why on a calculator you don't have the opportunity to change the base, because there's no need to. You have the change of base theorem. So on a calculator, you only have base 10 or base e, the ln, but nothing else. And consequently, the derivative of log base a, well, let's change from base a to base e. And this is going to be log base e of x over log base e of a. Or, if you prefer, ln x over ln a. And ln a now is just a constant. So you can pull that out. And all we need is the derivative of ln x. But we found the derivative of ln x to be 1 over x. And there you have it. Derivative of log base a of x is 1 over x ln a. How are we doing? Somebody was asking if I still have office hours tomorrow. I do. And Thursday as well. Connor is asking an excellent question. What if we did the inverse derivative trick? Wouldn't we get 1 over x again? Hopefully not. Shall we do it? So it's worthwhile to try. That would have been a good midterm question, in fact. You are not allowed to use L'Hopital's rule on the midterm. We have not seen L'Hopital's rule, so you're not allowed to use L'Hopital's rule on the midterm. In fact, you're not allowed to use anything we haven't done. Oh, sorry about that. I was in trouble signing in. Let me just take a moment here. Just a sec. I'll be right with you. All right, sorry about that. Yeah, Burnside 1127. Well, I mean, you can use it to confirm. Don't write it down. You know, I mean, on a separate piece of paper, you can do whatever you want. So it's a nice tool to have, but yeah. So Connor was asking about 10 to the x. If we use that inverse derivative business, the inverse function is log base 10 of x. So, I mean, according to this, the derivative of log base 10 of x should be 1 over x log 10. Let's check using this idea. If that's your function, you know the derivative is 10 to the x log 10, right? And I think we see where the logs are going to come from now. The derivative of the inverse we saw to be 1 over f prime of f inverse. F prime is this. F inverse is log base 10. So everywhere you see an x in your derivative, you replace with log base 10. So this is 10 to the log base 10 of x times log 10. And this simplifies to x once again. Everything is still the usual this week, tutorials and everything. Just because we have a midterm, nothing else is different. All right, so conclusion. In general, the derivative of log base a of x is 1 over x log a. Notice that this coincides if a is e, log of e is 1, and we're back to 1 over x for the derivative of log x. Let's do a few examples from the book. This is not midterm material. There we have it. You know what to do. Differentiate. So differentiate. Let's differentiate this. What do we have? X times ln x. So it's a product. Product rule applies. Differentiate the first one, leaving the second one fixed. Plus, leave the first one. Differentiate the second one. Derivative of ln x is 1 over x. Derivative of x is 1. X over x is 1. 1 minus 1 is 0. So we have just ln x as suggested by Yassine. Very nice. Rachel is asking, is the derivative of any inverse 1 over x? Well, I mean, I think we have the answer right here. Right? What do we have here? Here we have ln of something. So the derivative of ln is 1 over. So we'll have a 1 over sine squared. Jack is suggesting that the theory is much more complicated than the actual problems. So that's why I want you to concentrate on the actual problems first, get a good grasp of those, and then you can go back to the theory. How is log x and ln x related? They're related via change of base theorem. This is always true regardless of what base b you take. And if you, well, I mean, we're not done here, right? And if you take b to be e, you have the answer you're looking for. So derivative of ln is 1 over, and then we have to differentiate the inside, right? Chain rule kicks in. Derivative of sine squared, this is something squared. So 2 sine times the derivative of the inside, which is sine x. We do. I was just trying to answer a bunch of questions and left you with the feeling that we were done when we actually were not. Times the derivative of the inside, derivative of sine is cos. You can cancel one of the signs, leaving you with 2 cotangent. Let me point out that instead of differentiating immediately, you could have simplified the original function to begin with, using properties of the logarithm. Log of a power, you can bring the power down. And if you differentiated this, derivative of ln is 1 over, so 1 over sine x, times the derivative of the inside times cosine x, and you get exactly the same answer as expected. How did you differentiate sine squared? Well, it's something squared. So we differentiate the square first, we get 2 sine, and then you differentiate the inside. Could you use the product rule to differentiate sine squared? Treating it as sine times sine, and that's fine too. This scene is asking if we can use that as a rule. You can. It's fine. I mean, I would prefer that you understand that rule instead of just using it as a rule, because it's really just a chain rule, and that's what we're doing here, right? So I much prefer that you understand the chain rule than to apply that rule blindly. And as Suhail suggests, it's really just the chain rule. So if you're comfortable with the chain rule, there's absolutely no need for you to memorize that rule that you've given. Once again, let's simplify this, making use of the properties of the logarithm. This can be rewritten as 1/2 ln of x squared plus 1, making everything a lot simpler. And the derivative now, derivative of ln is 1 over times the derivative of the inside. There it is. Let's take an example. And let's talk about the derivative of ln of absolute value of x. We will do more inverse functions on Wednesday, Pratik, so let's postpone the discussion until then. Let's talk about the derivative of ln of absolute value of x. You will recall that absolute value of x is either x if x is bigger than or equal to 0, or negative x if x is less than 0, right? This nice piecewise function that we've been using over and over again. Jake would like us to redo this without simplification. Let's do it right after this. Right, so now you know that ln is not defined, right? I mean, the domain of ln is values bigger than or equal to 0. So the domain of absolute value of x, I mean the domain of ln of absolute value of x, is going to be everything except 0. So ln of absolute value of x is either going to be ln x, if x is bigger than 0, or it's going to be ln of negative x, if x is less than 0. Will there be any piecewise functions on the midterm? Absolutely. You can take that as a fact, even though I haven't written it yet. Rest assured there will be piecewise defined functions on the midterm. Lots of them. So many. So if we talk about the derivative of ln of absolute value, shouldn't those brackets be squared if 0 is not included? No. Round means not including. Why is 0 not in the domain? Look at your exponential function. Your exponential function is never 0. And the domain of the ln is the range of the exponential. So that's why. Right? I mean, we saw the graph. The graph of e to the x is this. And so the graph of the ln is this, not defined at 0. Well, I mean, this function is not defined at 0. So of course we cannot even talk about its derivative. So the derivative of ln of absolute value of x, well, you know the derivative of ln x is 1 over x. We saw that, right? And ln of absolute value of x is either going to be this or that. So if it's this, the derivative is 1 over x. What if it's that? The derivative of ln of negative x, what is that? Well, derivative of ln is 1 over, so that's 1 over negative x, times the derivative of the inside. Chain rule, right? Times negative 1, and these negatives cancel, leaving you with 1 over x as well. Eddie uses the square brackets going the wrong way. You know I hate that, Eddie. And web work hates that too. So try to adopt the round brackets. We're not going to mark it wrong on the exams, but it's unsightly, frankly. All right, conclusion. The derivative of ln of absolute value of x is always 1 over x. And you can do the same for the log in general. So actually log of absolute value of x is 1 over x ln a. Exactly that. How are we doing here? So that's the takeaway here. And I forget who was asking, perhaps Jack, to redo the question the other way without simplification first. So let's do that. What is the derivative of ln square root of x squared plus 1? Are we assuming that the derivative is continuous? We are not assuming anything. Andrew, this is not midterm material. Right? Derivative of ln is 1 over. Times the derivative of the inside. How come we don't have to do the limit thing here? You would need to do the limit thing if you were taking the derivative at the point where the function changes from one to the other, which would have been 0. But the function isn't even defined at 0. So there's no need. I mean, you would have needed to use a limit definition of the derivative if you were asking for the derivative at 0, which wouldn't make sense here because 0 is not even in the domain. So 1 over this times the derivative of the inside. But what's inside? Inside is the square root. Derivative of square root, 1/2. Blah, 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 to the negative 1/2 times the derivative of the inside times 2x. Chain rule again, right? And the 2's cancel out nicely. And you get, this is 1 over the square root times 1 over the square root. So the square roots disappear in the denominator. And you have an x on top. Exactly the answer we had before. How are we doing? Can we explain the purpose of the limit definition of the derivative? Well, you're thinking to yourself, we have all of these rules for the derivative. Why bother with the limit definition? It's a valid question. But where did all of these rules come from? They came from the limit definition. If you don't have the limit definition, you have nothing. You don't have any of these rules. You don't have anything. All of these rules, the product rule, quotient rule, chain rule, power rule, the derivative of a sum is the sum of the derivatives. These all come from the limit definition. Moreover, as suggested, if you have a piecewise defined function, the only way you can guarantee the existence of the derivative at the point where the function changes is using the limit definition. So limit definition is of tremendous importance. And if I ask you to differentiate a function using the definition, then I want you to use it, to differentiate it using the limit definition, not using those rules. Because, again, everything comes from that limit definition. Tremendously important. So let's not underestimate it. Questions? How are we doing? Practice this derivative of logs business. We'll pick this up again on Wednesday. Thank you all for coming. And move away from that closed brackets going the wrong way. I'll see you guys on Wednesday.